Okay, now we're going to do the same thing, but we're going to use the plugin. That means we don't have a node running a PD controller anymore. So this is a more advanced way of running a controller. Gazebo plugins by default, now you can change this, can run at full rate in the Gazebo simulator. At least for Gazebo 2, that's considered 1 kilohertz. And here we don't publish anything. It's running directly in the plugin. Do you know what a plugin is? It's a library that can be loaded dynamically. Yeah, so it's going to be a .so file, but it works within the Gazebo ecosystem. So Gazebo loads these libraries into Gazebo. Okay? Now, we're going to also use ROS control and ROS controllers. These are packages, ROS control and ROS controllers. So ROS controllers in Gazebo have interfaces that are identical to the actual hardware. These packages are designed to make controllers work the same in simulators and in hardware and expand them. So the dynamic behavior in simulation would be similar to the hardware. Okay? Not exactly the same, but similar. However, and ROS control and ROS controllers were designed to be general and extensible, but they're complicated. They're not that simple to manage. And then in page 130, you can see that they depend on other packages that you need to download. Now, if you use the script in this book to install the packages, you have already downloaded those dependencies. But you can refer to this page to look for more. Here's a link, ROS control, joint controllers with Gazebo for reference. And right now what we're going to need to do is do 5 steps to set the ROS joint controller as a plugin in Gazebo. Number 1, in the URDF file, we need to include limits for 2 things, the joints and the torques. Otherwise, this plugin will not work. In the URDF file, we need to say for every joint that we have, what are the limits of that joint? Normally, you would have that information available from the manufacturer. Also the torque limits. Then you need a field or a block, a transmission block for each joint. For example, if you have 6 joints, you'll have 6 transmission blocks for each joint. The transmission is something about how does motion from the actuator translate into the link. Because we normally use gears or harmonic drives, and there's a transmission ratio from one to the other. Yeah, when the motor moves like this, maybe the arm moves like this. So we need to encode that transmission ratio. For these examples, we're going to use a value of 1. But again, your manufacturer would tell you what that number is. Then we need a Gazebo block. In this Gazebo block, we tell what plugin we're going to use. For now, we're going to use the plugin called libgazebo ROS control. This is the plugin that we use for PID control of a joint. For your homework, you're going to use a different plugin to control a mobile robot with 2 wheels. It's called a differential drive plugin. Then, because we're using a controller is a PID controller. There are some values that we need to set. What are those? The PID gains, and in case of the integral term, the I, we also have something called clamping values, the maximum and the minimum clamping values. So for each joint, we need to set these values. And for that, we need a YAML file, Y-A-M-L, YAML file. And then we need a launch file where we set everything up. Number 1, we load the controller parameters from the file into the ROS parameter server. And then we use one of the packages from ROS control to start the controller. Let's look at the details. So now in this file, minimal robot description with joint control.urdf, we're going to have 3 new blocks and we're going to study that. So let's take a look at this file, and we're going to look at the joint block with the limits, the transmission block, and the gazebo block. Let me maximize this window. Raw set. Actually, we're right here. So, oh no, raw CD, minimal robot description, Emacs, and minimal robot description with joint control.urdf. I have an alias that puts color into this. Actually, sorry, it just opens in this window quickly, like that. So let's take a look. Here's our normal link. Here's the link block. Here's our normal collision as before. A collision block, visual block, inertial block. And then we have link 2, finishes here. And then down here for our joint, we have joint 1, type revolute. We have the parent, the child, the origin, and the axis as before, but look, now we have limits. And these limits for the effort will be set to 10 Newton meters. Yeah, this is torques. These are the position limits, the lower position joint angle and the upper position joint angle in radians, and the velocity limit, radians per second. Radians per second. How many? The angular velocity in radians per second. So it cannot move faster than this. That's our joint block. And then here we have the transmission block.
What's the dynamics thing?
Oh, damping. Yeah, sorry, I forgot that. So damping is related to the friction of the joint. Something about the friction of the joint. It slows the joint down. Because joints have friction, right? So there's something working against the motion of the joint. And this number acts to slow you down. In your homework, you will change this value around to study the response of the robot with different values. But it's something that dampens the motion and slows down the motion. The bigger this number is, the harder it is to move. Yeah, that's a friction component. Of course, none of these are easy to find perfectly, right? It needs experimentation to know these values. A lot of physics behind this. Then here's a transmission block. We have a name, and then we have a type and a hardware interface. For now, ROS control only has one type and one hardware interface, I think, implemented. So this would always stay the same. It's a simple transmission, and it's an effort joint interface. Like you send a torque, and it returns a joint angle. Yeah. And we have a name of the name of the joint upon which this transmission is working. Transmissions work with actuators, the actual motor. Yeah. So here you can create a name simple like this, motor 1, effort joint interface, and this is the gear reduction. So this number is something that a manufacturer would tell you. It's depending on the connection of the joint and the actuator. Yeah, like again, a motor might move just a little bit, but the arm might move a lot more, depending on that reduction. And finally, we have the gazebo block, and this is where we say the plugin. We give it a name, gazebo ROS control, but the name is this one right here. When you download the binaries for gazebo, sudo apt-get install, ROS Indigo, ROS control, this will get installed in OPT share. Yeah, so it's going to be able to find it. And then this robot namespace is very important. Look at this namespace right here. This namespace is designed to give a name to your robot. Yeah. So anytime you are publishing or subscribing from Gazebo, it'll say one DOF robot at first for different things. You'll see how it works. But this namespace is very important. You'll need it in your controller parameter file. This is the name of your robot namespace. And you'll also need it in the launch file. Write that down. No one is taking notes. Yeah, I'm going to emphasize that later here, but it's important. Okay, so if we want Gazebo to work with the plugin, we need to add these three things, right? For every joint. When we use Baxter, you'll see that this is repeated 7 times for each arm, and also for the head, and also for the hands. Okay, so the files get quite a bit bigger. And like I said, this namespace name is very important. Now let's look at this controller parameter YAML file. If we go back to minimal description, yeah, normally in every package, this is just for example, but in every package you'll have a folder called config. In this case you called it control config, but normally it's going to be config. And inside the config folder, you're always going to have YAML files. YAML files are files that contain data for parameters. Last time in our launch file, we saw how we set one file to robot description, right? But that's just one parameter. What if you want to load 15 parameters? You don't want to do that one by one. You can do that putting those 15 parameters in one file and then just loading one file. Let's look at this file. One DOF control parameters. YAML. So look at how this file starts with the robot namespace, okay? With the robot namespace. Where did we put this name? Oh guys, come on, I just emphasized it. This name is in the Gazebo block.
Yeah.
Robot namespace.
Developer namespace.
Yeah, I just told you this namespace is very important. It's going to go into the controller param file. And then I show you that file and you were like, okay, now here we have 2 comments. Publish the joint states and then something about position controllers. Remember, a controller always has 2 parts. One is the feedback, the joint states. What is the state of my joint? The positions, the velocities, and the torques. And then there's always the command or the reference. Where do I want you to go? So here, these names are important. We'll see them in a second. Joint state controller. This is the name of the controller for joint states. And we need to give the type. Joint state controller, joint state controller. And here, what we do is say we have a rate of 50. For position controllers, we use this name, joint 1, position controller. And then we have the type, effort controllers, joint position controller. We have a joint name, and then we have the PID values. This value is hard to set. You normally want to start without it. You might have a value of 0 there. If this is a value of 0, this can be 0, and this is 0. But if you have a value here, then you need a minimum and a maximum clamp. Because you may not know a lot about PID, but when you use the integral term, the error can accumulate so much that actually it hurts you when there's a over accumulation of error. So you need a maximum and a minimum limit. Okay? And so we have a controller for each joint. We need to say the type, the name, the PID gains, and the limits. Tuning PID gains is challenging in general, and in ROS, an easy way, the best way to do it is by using RQT reconfigure. We haven't studied RQT reconfigure yet. There's a link here, but it's how to change parameters online. So you change the p-value and you tell the robot to move in the simulator, and you see the response, change it again, until you get something that is more stable. Okay. By default, the libgazebo plugin will have an interface with RQT reconfigure, so you can use that easily. Now, how do we get this started? Number one, the controller files need to be loaded to the parameter server. We're going to do this in this launch file. The launch file will load the YAML config file to the parameter server. These are parameters that are used by the joint controller later. The joint controller, where is it? Where is the joint controller?
YAML file.
No, those are the parameters, the PID parameters, and some types. Where is the controller running? The PID controller, where is it running? Yes, and the plugin. Yeah, the plugin will be set to load these values in the way that we set them in this file very specifically. After that, we load the robot URDF to the parameter server, robot description. Start gazebo, spawn the robot into gazebo by using the model in the parameter server, and start the controller plugin by using the controller manager package and the spawner node. This is new for you. So there's a package called controller manager. Yeah? And then when we spawn the node using this namespace, the same one from the gazebo block, it will then start the controller. It will look for the types of controllers that we defined, and then it will start doing the PID control. Let's take a look at the launch file. Oh, no, that's the name. Minimal robot with control. Oh, it's still not good. Okay, so let's see. So we load the joint controller configurations from the YAML file to the parameter server. Yeah, so we say ROS param. But ROS param is different from param that we used before. ROS param is a tag that looks for YAML files. YAML files. So when you use ROS param, you need to give it a file with a YAML extension. Got it? So we say, what's the file? We need to give it the path, find, minimal robot description, control config, one.control control parameters.yaml. Command equals load. So this whole thing here is going to load all these parameters. Number two, let's load the URDF into the parameter server, into the parameter called robot description. So here's the file with joint control.urdf. Goes into the parameter server. Now here we are not opening gazebo by ourselves. We can include that line easily. So we'll start gazebo first, then we will run this launch file. So we say gazebo ROS, spawn model, arguments, parameter server, robot description parameter, URDF type, model, one.robot. Oh, here it is. Here we start gazebo. Maybe yours doesn't have this. Maybe I changed this at home recently to make it easier. But you can start gazebo first and then run this one.
Okay.
Yeah. This will start gazebo. And then we're going to start up the controller plugin via the controller manager. So we give it a name, controller spawner, package, very important, controller manager, the type, spawner. Respawn means if something fails, do you want to try again? And here we're saying, no, we don't want to try again. Output equals screen. This means any ROS info messages. If you want them to show up in the terminal, then you need to say output equals screen. This is when we say ROS info, ROS warn. In order for them to show up on the screen using a launch file, we need to say output equals screen. Namespace, very important. The namespace from the gazebo block. Yeah? And then arguments. These arguments are the names of the controllers that we used in the controller param YAML file. For example, let me see. I'll show you in a second. But this is join state controller and join one position controller. Do you remember these names? No? From the YAML file. Let me change to that. Control config. One-DOF control parameters. See this name? Join state controller. Join one position controller. You see these two names? Those are the arguments here. Join state controller. Join one position controller. Yes or no? Here. The name of the controller, the name of the controller. Those names are created by you. And then you need to pass those as controller names. Sometimes we will have position controllers, velocity controllers, effort controllers. And sometimes you'll have them for each joint. So Baxter has 7, right? So you need to put a list of 7 controllers, maybe plus the joint state. Yeah? This list can get very long. You can compare this to Baxter files for those of you that have some experience to see how this looks for a more complicated robot. All right? So we'll close this and we'll close gazebo. Okay, and we'll close this RQT file. We'll close this topic. And I think that's it. So now we can try to launch this file. So let me, actually, let me do one thing real quick. Oh, I did comment this out. Yeah, that's important because we want to do it separately. Okay, so the first thing I'm going to do is, let me close these windows for now. Close this one and close this one. Make this one small. Well, let me see. Let's start gazebo first. Okay, here's gazebo coming up. I'll minimize this. And here we're going to launch the launch file. ROS launch, minimal robot description. And let's look at the output that comes from these messages, okay? The output is important for you guys. Okay, so here, loading gazebo ROS control plugin. Yeah, loading the plugin as soon as we had that from the launch file. Then, after you load, starting gazebo ROS control plugin in namespace 1DOF robot. Okay? So you load it and then you start it. Gazebo ROS control plugin is waiting for model URDF and parameter robot description on the ROS parameter server. And we provided that, and then loaded gazebo ROS control. That's what's going to control the robot. Then down here, we have controller spawner, waiting for server, controller manager, load controller. Yeah, that's what we just used to launch the plugin. Waiting, and then loaded controller, joint state controller. Loading controller, joint 1 position controller. Now, yeah, loaded controllers, this one and this one. And after you load the controllers, you can start them. So right now they are working. Okay, they are working. So now in Gazebo we have this, but we have these controllers running, right? And we can go back. Let me maximize this empty window. And we can say raw service list. Now look at all these new services with one DOF robot. And they're followed by controller manager for the most part, except this one. Join 1 position controller PID set parameters. So if you want, you can have a service that changes the PID values. Yeah, but that's why RQT reconfigure works, because it's actually sending values to this service right here. And you do it automatically. Right now we have to do it manually if we use this directly. We have list controllers. So for example, we could call this and get a list of the controllers. I think we can just do this. I just say raw service call and call the service topic, and it says, hey, let me tell you what controllers you have. Join state controller, join 1 position controller. It's running. Here's the type. This type comes from our configuration file. Here's the type. Here's the hardware interface. And here's the resources. Okay? So I just called it. It's a service to list the controllers. And then if you want to load controllers, you need to give the name of the controller. Because sometimes, let's say we have position, velocity, and effort controllers. Sometimes you'll say, I want to use position. So you load them and start them. Or actually, there's another thing called switch, which you can see here. You may be in position and you say, I want to switch to a velocity controller. When you switch, you stop the previous controller, unload it, load the new controller, and start it. That's how ROS control works. This is about ROS control. Okay? Now, I haven't shown you the picture yet. In last week's Gazebo presentation that I sent you as an additional PDF, there I have explanation of ROS control with Gazebo. So if you've studied that, you might be more aware of what's going on. My sense is you have not looked at it, because a lot of you look very confused. When I give you something, please try to look at it. Otherwise, you get behind. Yeah? I know it's a lot of material. This is not an easy part of ROS. Okay, so this is what we have here. We can also look at the ROS topic lists, and you might get a different list. Join 1 position controller command. This is where we're going to send the joint angle command. Yeah, like we did before, but this topic is coming from the plugin, not from ourselves. Okay? We have 2 topics for PID, parameter updates, descriptions, and then this is join 1 state, and then this is join states. They're a little bit different, both of them. The join 1 state will give you the position, velocity, and effort. The joint states will give you position, velocity, and effort for all the joints. But the join 1 position controller state, that will give you information about the PID gains. These are both state, right? And they have the word joint, but what's the difference? This one has controller. So you get information about the controller, PID, values, things like that. This one gives you position, velocity, effort for all joints. Yeah, we can take a look. These are topics, right? So we come back here. We can say ROS topic, list. Okay, here's joint one state, so we can say ROS topic what? Echo, let's do it just one time, not many times. Number one, number of times to do that. We do this. So here's PID and the clamp, time step, error, process value, set point. And everything related to the controller, the goal, the error, and the parameters. If I use joint states, and by the way, this is for one joint. If we have more than one joint, actually this is for joint one. If we have more joints, we get more topics like this one. Joint 1, joint 2, joint 3, or whatever name we use for that. If we do the same thing for joint states, you get the name of the joint and then position, velocity, and effort. Okay? So now what we're going to do, as before, is examine the dynamic response. We're going to use RQT plot like before, but now look, we need to go to the namespace, joint states, position 0, velocity 0, effort 0. Yeah, a little bit longer. And then we can command to join one position controller command, and then we'll see this response, okay? So let's see how this works. Let's move this over here. Zoom in a little bit. Let's bring out our message over here, our terminal. So here, RQT plot. Yeah. RQT plot, let me see. That's a long name. One DOF robot joint states.
F or 0 means like every.
Yes. Like that. Let me copy this and paste. Velocity 0 and effort. Okay. If there's an error, it won't show you, but this loaded okay. Yeah, let's minimize that window a little bit. Maybe put it around here. And let me change windows. I need to open a new one. And then we're gonna launch, right? Oh no, make the manual command. ROS topic pub, one-off robot joint. No, what is it? Need to look here. Rate of 10, joint 1 position controller. What is it? Why doesn't it? Joint 1 position controller, command 1.0, and we'll do this at a rate of 10. Okay, ready? And look at how it's moving. Why is that? PID control. Yeah, so actually here you can choose the zoom in version, but zoom out. Actually, I don't. Let me try this again. Let it run. Let's make this small. Let's send this back to 0 and back to 1. I want you to see the full response one more time. So it goes back, and then back to 1. Slow PID response, right? That means it's a bad controller. That means the gains are not tuned properly. That's what that means. So we get this response right here. We can zoom in into it. Yeah, we have something like this. Position is blue, so goes up, goes down, goes up, goes down. Yeah, that's a very bad controller. There's a lot of oscillation. You want something that goes kind of in a straight line to the set point. And then the velocity will has the same response, and the effort also has this variation. So it doesn't reach the set point quickly and stay there. We could increase the P and the D parameters to try to improve the response. Yep, this is about control. Okay, but we won't describe this in detail for now. All right, so I'll close this and kill the rest. But what have we done now? We have integrated a controller through the lib gazebo ROS control plugin. URDF, gazebo, ROS control together. Okay, and this is a great way to do things.